Here we are once again. It's the physics video lecture, Physics 203, video lecture 10. And we're working on the central force problem now. So this is some great stuff. We're going to take it all the way through to the Kepler problem and do some scattering and other interesting things as well. So I'll remind us where we were. We started with two bodies, M1 and M2, and their positions. And we defined this difference vector, which can be expressed in terms of the original two vectors as well. And we were able to get the differential equation for that difference vector equal to F, like that. Now, in this case, the mass was what's called the reduced mass, the product of the two masses divided by their sum. But this is an effective one-body problem. So it's true for a central force problem that just happens to have a single body, even though we generated it from a two-body problem. And we had then found that the angular momentum is also conserved. Which we already had from our conservation laws discussion a couple times. We've already had that. But the next point is that we're going to be able to write this in terms of plane polar coordinates. So therefore, from the angular momentum being conserved and these two vectors always being in a plane, so the position, the velocity are always in a plane that's perpendicular to the constant angular momentum vector. So the motion is restricted to a plane. So motion is restricted to a plane, and therefore we can use plane polar coordinates. So that's where we're going to start. And those will be r in feet. Now, we're doing Lagrangian mechanics, so we need a kinetic energy and a potential energy. Okay? We don't actually have to begin with Newton's law. We have these conservation laws, plane polar coordinates. So let's see. So next we're going to construct the Lagrangian T minus U, the kinetic minus the potential energy. And this will be 1/2 mass r dot squared plus r squared v dot squared, like polar coordinates, kinetic energy. And for the potential energy, we're just saying it is a function of this r, which is the separation distance in our original problem. And this gives us a central force. So we have gradient minus gradient u of r is equal to u prime of r minus u prime of r times that unit vector, which is the force. So another way to put this would have been, and I'll go ahead and fill it in right here, since we're talking about a central force and not just any old, and that was already implicit in the construction, okay, central force. This can be thought of as the magnitude of the force and its unit vector direction. Okay. So that u prime minus u prime is just that f right there. So good, we have the Lagrangian. of course, we could get the equations of motion from the Lagrangian. They would be in R and phi. And those would be the same equations of motion you get if you remember your plane polar coordinates and the component-wise radial and angular equation here, which is actually a little more complicated to get. It's nice that the Euler-Lagrange equations will just get them to us, no problem. Okay. So what do we have now? We have a Lagrangian and we have conserved quantities. So energy E and angular momentum L are conserved. All right, we just started with L being conserved. This is the magnitude of that angular momentum. Now we know that dl d phi dot is m r squared phi dot. That is this L right there, the conserved quantity with respect to angle. The energy is sum of dl dqi dot qi dot minus L. In general, in this type of Lagrangian, it is simply t plus u. And so we also have that being conserved. I'm going to put these both in a red box. So t plus u, we have t minus u, so E is t plus u. So we have 1/2 m r dot squared, r squared t dot squared, minus u of r is equal to E. So these are our two conserved quantities. When you write them down, what you also see is that we have two differential equations. These are, of course, differential equations, d phi dt, dr dt. They're coupled, but we have two first-order differential equations. So this is the route, really the only route to the solution of this central force problem. So I'll put this important note. These are two first order differential equations. And before we solve the problems that we want to solve, say, before we get a complete solution to the differential equation, we want to analyze them and figure out what can we know without solving them. Okay. So the next task is to analyze those. Yeah. So what we're going to do next is plug phi dot from this equation into here, and we will obtain an equation that only depends on R. So next we'll take, so taking phi dot equals L over m r squared into the energy, we obtain 1/2 m r dot squared plus L squared over 2m r squared plus u of r is equal to E. Right? R squared phi dot m r squared phi dot squared turns right into here. Okay, this. And this, you guys may recall and recognize, is what we call the effective potential. So this, as written here, is effectively a one-dimensional problem because it only has this one dynamical variable R. It's called the effective potential. And I'll go ahead and write it this way: 1/2 m r dot squared plus u effective of r is equal to E. Now, everything we know about solving one-dimensional problems, one degree of freedom problems, is available to us to discuss this thing. In fact, you can see right now we can already reduce this to a quadrature. In other words, we could just separate variables and get t as a function of r, and if we're lucky, we could get r as a function of t. So the idea with this effective potential is that if you take this term here, which came from the kinetic energy, okay, it didn't come from the potential energy, it comes from the kinetic energy, if you just add it to the potential energy, you get a function of r, and you can treat this as a one-dimensional problem. Okay, it's still part of the kinetic energy, but formally we have a one-dimensional problem. So that's the significance of obtaining this effective potential. Very useful. So, right, effectively a one-dimensional problem. So that's why we call it the effective potential. So now I'll remind us of how we deal with one-dimensional problems with a potential energy. We just change the name to R. But other than that, we've studied this before. So one-dimensional systems with a potential energy. What we generally do is we have a U, and since we have an effective potential, we're just going to call it that. You know, it was U of X, now it's U of R. So suppose we had a potential energy that looks like that. Okay. Actually, how about we extend it, make it a little more interesting. So it's got, in fact, you know, I'm always teaching the roller coaster. Let's make this a roller coaster. There we go. A little roller coaster potential energy. Except now it's R instead of X. So depending upon your energies, here we could have a stable equilibrium. I'm just going to say R1. Here at R2 we could have an unstable equilibrium. And this equilibrium would hold for energies less than this one I'm marking off right here. So I could call this E1. I'll just call it E right now. So you have certain energy. As long as the energy is less than that, I have to call it something. I'll call it E0. As long as you have the energy less than that, you'd say you have bounded motion. Now, if you started out here with an energy less, so started out here, you'd have an unbounded motion because you'd be going out to infinity. If you had an energy at this high level here, I'll just put a star right there, you'd have a motion that goes down here and keeps going. So your intuitions with the roller coaster are just good for one-dimensional systems, right? If you're down, if you have energy indicating that you started at this point, you're just going to go back and forth in here, and so forth. So we inherit all of these things with our central force formalism here as well. What we have to remember when we're doing this, we're talking about, we're investigating the one-dimensional problem. We have to keep in the back of our mind that there is this angular behavior going on at the same time. So, okay, this was a one-dimensional discussion from the roller coaster. I don't even write that down here. Example, roller coaster. Because in the elementary classes, I'll just do the roller coaster and talk about conservation of energy. And right, that discussion is germane here as well. Okay, so I'll use this part of the board. Now we're back to our central force one, so we're going to treat it a little more carefully. This is U effective versus R. And I'm going to, let's write some examples first. And then we'll graph them. So U of R equals 1/2 K R squared. That's certainly a possibility. We could, for example, have had, forget this graph for the moment. We could have had two masses connected by a spring, M1, M2, and K, and then we would have had U of R equals 1/2 K R minus, gotta use a different letter than L, say R minus some relaxed length A squared, right? That would be two masses on a spring, relaxed length A. And we can also imagine a 1/2 KR squared from the central force potential. The other example, I'm gonna number these, is the one we're after for real, so to speak, and that would be the Newton potential. U of R is equal to minus alpha over R, where alpha is gravitational constant product of the masses, R is the separation distance. So let's graph over the effective potentials for these two problems here. And then analyze them a bit. So what we're looking at in the first case is U effective equals L squared over 2mr squared. Remember, that's always what is brought into play. Okay? L squared over 2mr squared plus 1/2 kr squared. Here we'll do some dotted lines. So the L squared over 2mr squared always has this generic form. Okay, 1 over r squared. The 1/2 kr squared is a parabola. And so what we end up with here is a function that looks like this. And it clearly has a local minimum that you can find. And given certain energy levels, there's R sub 0. I'm going to actually indicate E sub 0 here, and then an E sub 1. So my E sub 0 is the minimum energy. Now, in the one-dimensional world, we would just be sitting at the bottom of a potential well, at the bottom, bottom of the roller coaster. We'd just be sitting there with this energy E sub 0. In our problem, though, we have that angular momentum. So what this represents is actually a circular orbit. So E sub 0 is equal to the minimum energy available, in this thing. So if you minimize this function here, it's equal to U effective of R sub 0, minimum possible energy. But instead of just sitting there, with m r sub 0 squared phi dot is equal to L. So look, we now have a constant radius and L, so phi dot I can also call omega sub phi. That's now an angular frequency or an angular velocity. Omega sub phi would be equal to L over m r naught squared equals constant. That's uniform circular motion. So that's the discussion of E sub 0. We also want to talk about E sub 1. Keep labeling this thing. So along with E sub 1, we have an R min, and taking this energy level over to here, an R max. Okay. So the motion is restricted to values between R min and R max. So this was point 1 of this discussion. Point 2 is going to be E equals E sub 1. So R min less than or equal to R less than or equal to R max. Now phi dot this time is equal to L over m R squared, and R is no longer constant. But from our one-dimensional motion, we see that there's an oscillation between R min and R max. An oscillation, but at the same time, the angle is changing. So let's make sure we write that down. So R oscillates between these values. And at the same time, a little more room here, phi dot equals L over m R squared is again the angular motion. So what that means dynamically is that we draw two circles. One has an R min and one as an R max, and the motion is then restricted to this annulus, because as the radius is changing, the angle is changing as well. So angle phi changes as radius R changes. And so we're going to get some kind of orbit here. This one was uniform circular. This one, it all depends. It could, let me try that again. It could be a closed orbit, but it does not have to be. So closed orbit would sweep out from R min to R max, and then back from R max to R min. But it doesn't have to be closed. So we'll make sure we note that. We're going to calculate cases where it's closed and where it's not closed. Orbit does not have to be closed. Okay. So this is the discussion of half kr squared for the potential, and then the entire thing is the effective potential. Now the Kepler or the Newton potential is also really interesting. So point 3 of this discussion is the Newton, where we have U of R equal to minus alpha over R. We'll just always do that for simplicity. Of course, that's for simplicity. If you have a two-body problem, it's Newton's law. If you have something else, it's just minus alpha over R. You could also have charged electromagnetic charged particles. Then you could have attraction and repulsion. But good, let's go ahead and graph the effective potential. For this one, we have L squared over 2mr squared minus alpha over R. So this is an interesting one. Room to do it right here. So you actually want to leave some room underneath, because what you have is two branches here. The 1 over r squared is as before, but now we have a minus alpha over r, and that would be of that type. So you might wonder who wins, but in fact for small r, this left term is going to dominate. So in the limit as r goes to 0, this one dominates. In the limit as r goes to infinity, this one dominates. And the combination of those two behaviors tells us that our effective potential has this form. Okay, like that. And this is really interesting now. We see we have a local minimum and the corresponding energy, and that would be a circular orbit. But then we have bounded orbits as long as the energy is less than 0, and if energy is greater than 0, they're unbounded. So E0, circular orbits as before. How about E0 less than E less than 0, so negative energies, bounded orbits, and E greater than 0, unbounded. And these we'll see are the famous elliptical orbits of Kepler, and unbounded ones are the hyperbolas. Circular orbits are a limiting case of the ellipse. And the E strictly equal to 0, one could show that they're parabolas. So there's the discussion of the effective potential in all three of these two cases here. But did we have three energies here? Here we only had two energies, okay, because it was bounded in both directions, but here we have the unbounded aspect as well. So we got these three right here. Have a look at the clock. Okay. So we just mentioned the Kepler problem, and that's what we're going to discuss next. Good. the Kepler problem. So the Kepler problem was for Isaac Newton to show that using his law of gravity, and after all, our equations are essentially Newton's law of gravity, plane polar coordinates, to show that he could reproduce the Kepler's three laws. So, obtain Kepler's laws. Now, you know, I should actually point out, you see, Newton had used Kepler's laws, Kepler's third law in particular, to derive his, or to discover his law of gravity. So, he then had to go out, go back into his formalism, Newton's laws, his old dynamical formalism, and of course, trivially, he's going to obtain Kepler's third law, but he has to obtain Kepler's first and second laws as well. So we're going to approach this from a couple of directions. And the first one, we're just going to do the direct integration. So we want to obtain Kepler's laws, and we're now beginning with mr squared phi dot is equal to L. It's a conservation of angular momentum. And 1/2 m r dot squared plus L squared over 2 mr squared minus alpha over r, right? That's the effective potential we just discussed, equals E. Now this has already been separated or reduced to a single dynamical variable, but we want to obtain Kepler's laws, and that had to do with the orbits of the planets. So we actually have to combine these two equations in some way. And what we want to do is find phi of r, or r of phi. So find orbital equation r equals r of phi. So we'll do this in a couple of steps, and then I'll hand it over to you guys to finish. So to find r of phi, first we're going to write out the separation of variables for this equation right here. So we have dr over dt is equal to 2 over m. Then we just take E minus L squared over 2 mr squared minus alpha over r. Close parentheses. We're taking the square root and plus minus. So there's our dr. Now what we can do is from equation 1, we can write d phi over dt is equal to L over mr squared, and we're just going to substitute. So from the first equation, we have dt is equal to d phi mr squared over L. Okay, just by cross multiplying. And then we can make that substitution. So we have dr divided by dt. So dr times L. Okay. So dr do this in 2 steps. So we got the dt is d phi mr squared. Equals plus minus this thing. So we'll do one more step. We've got room right here. So there's the d phi. We're going to separate by bringing the r's to one side, the phi to the other. Make sure we've got room right here. So we have dr divided by plus minus 2 over m e minus the u effective. And here we have L over mr squared. Okay. Make sure we don't mess this up. So the dr is in the numerator, okay? L over mr squared. And over here we have d phi. So if we can do this integral, we'll have phi of r, and if we can do the integral and invert the result, we'll have our r of phi. Yeah. So yeah, and what we'll be primarily interested in is energies less than 0, which will give us the circular orbits and the bounded orbits. So actually, I'm going to rewrite this again. And then I'm going to have you guys do this. So what we have is the following. We have phi is equal to the integral dr L over mr squared is a good way to write it. Okay. And then we've got the plus minus here. We've got 2 over m e minus L squared over 2mr squared minus m minus plus, so plus alpha over r square root. So yeah, this is the integral that has to be solved to solve the Kepler problem. And a couple of substitutions and you have an inverse cosine. So I want everybody to do this because it's good practice, and then you can actually say you've done this problem. So let's see here. We'll get the ball rolling. We're going to let u be equal to 1 over r, du is equal to minus 1 over r squared, dr. Okay. I'll go over here to the right. So then we have plus minus or minus plus. See, we've got the dr over r squared right here, so we have L over m du, and here we have 2 over m e, I'm going to write plus alpha over r minus L squared. Oh, we already did the substitution. So we have e plus alpha u minus L squared over 2m u squared. So there are a couple of ways to go now, but if you divide top and bottom by L over m, you're going to clean it up. And then to obtain that inverse cosine, there's a complete the squares trick. There are a couple of tricks here. Let's see how we're doing for time. we can do this. We've got du, and then we can write m over L in the denominator, so we've got 2 over m, and if we take it under the square root, we'd have m squared over L squared, and we'd multiply it through with this e plus alpha u minus L squared over 2m u squared. And that's going to give it a good form, because this L squared over 2m will cancel against this L squared over 2m, right? We've got this one gone already. So we'll have plus minus integral du we'll have 2e m over L squared and we'll have plus 2m alpha over L squared u minus u squared. Okay, we're still not seeing an inverse cosine, but actually if you went to an integral table, you'd find an inverse cosine and they'd tell you how to deal with all these coefficients here. You can obtain it yourself if you do a couple of substitutions. I'm going to put dot, dot, dot here. Let's see. Let me set this up. So here's where I write homework equals homework, and take it from the top when you write it out, because once you get this integral, you're going to be pleased. So equals homework. So dot, dot, dot. What we're looking for is the form like this. When all is said and done, you do a couple of substitutions. There's a complete the square trick down here. You can get it in the form dw root 1 minus w squared. And there's your inverse cosine, and then you work your way backwards again. Work your way back to where you started with this substitution and a couple of more substitutions. Equals inverse cosine of stuff, right? Once you have that, you can get r of phi, because you have that w, and the w contains the 1 over r, which contains the u, which is the 1 over r. So you work your way back. So that's a homework. And a couple interesting tricks along the way. But when you get there, all right, finally obtain r of phi is equal to p over 1 plus e cos phi. P is called the parameter, and to check that you got the right value for it, you'll notice that when e is equal to 0, this is another constant. When e is equal to 0, r of phi is constant. So p is called the parameter. It's equal to the radius of the circular orbit. Radius of the circular orbit. So if you take your effective potential, which is not up here right now, right? So you take your effective potential, set it equal to 0, solve for the circular orbit. Set the derivative of effective potential equal to 0, solve for the orbit, and that is what this constant should turn out to be. And E is called the eccentricity. So got this. E is the eccentricity. And you can find that as well. But this form here, right, and those are kind of complicated constants because they contain all of this, okay, all of this stuff. But you want to know those and then be able to study the orbital equation in this form, which is very simple, okay? And let's see, if we have time, I'll do a little discussion of that. Yeah, we have plenty of time. So yeah, you want to go through all these steps, get an equation of this form. All right, hint, complete the square. Right, because you want a constant plus something or minus something squared that will eventually lead you to this form here. Yeah, this is, and of course you can find this everywhere. This is the standard result for the orbital equation. Parameter, eccentricity. So you can definitely look those up as well and work your way backwards. But you definitely want to get that integral because it's very satisfying to get this whole answer. So what we want to do next is study what this means. And I'll use the board right here to the left. And then I'll set up another problem for you. So there's our equation, and we want to graph orbital equation for E less than 1, right? If the eccentricity is greater than 1, you're going to get the denominator to vanish and you'll have those unbounded equations. So E less than 1 corresponds to energy less than 0. Okay, that's an important point. So suppose we want to graph this. What we have to do is note that x equals r cos phi. Remember we started with plane polar coordinates, r sine phi, and we have this r of phi equals p over 1 plus e cos phi. So those are our ingredients. You guys are going to supply what p and e are equal to. But now let's make a decent sized graph. In fact, this should be a page filler. Okay, so p is a constant, e is a constant that's less than 1. So when phi is equal to 0, right, here's our x and y axis. When phi is equal to 0, we have r is simply equal to 1 plus p over 1 plus e. And when phi is equal to pi, p over 1 plus e cos pi. So p over 1 minus e. So over here we have minus p over 1 minus e. Okay. And when phi is equal to plus or minus pi over 2, the cosine vanishes and we just have that number p. So we would have p and minus p. And we're going to get an orbit out of it. Now notice that this is greater magnitude-wise than this right here. So we'll put a little star here. The geometrical center of the orbit is on the midpoint between those things here, and this drawing is not so good. I'll exaggerate that distance a little better. So we'll get good luck. There's your Kepler ellipse. That's your Kepler ellipse. Okay, you guys can draw a better one. So we still have to label this, and we're going to have semi-major axis 2A and semi-minor axis 2B. So it's longer in this direction than it is in that direction. And like I said, you can see by construction here, that's a 1 plus E, that the geometrical center is somewhere to the left here, so it's not at the origin, right? This is our Cartesian coordinate system. There's that origin right there. But the center of the ellipse is not at the origin. Yeah, what is at the origin? That's your center of potential, right? That's what your central force is with respect to, because this R here is the distance from here to any point on the orbit. Okay. So yeah, I'll just put this here. Star is the geometrical center, but it's not the dynamical center. It's the geometrical center in this picture here. Origin is the center of force, we could call it. Right? That's what the force vector is pointing to for an orbiting object. Right? So if you have an orbiting object here, the force is pointing towards the origin of our Cartesian coordinate system. Just so we don't mix those things up. Okay, let's check the clock again. All right, let's see what's next. So we get that. Like I said, you can look these up and then work backwards and make sure you get that integration. So our next task, and I'm going to assign that as well, is to prove that this here really is an ellipse. Now a math book will tell you that's the polar form of the conic section, so in that sense you know it's an ellipse, but we want to prove that our standard ellipse formula is satisfied by this here. So we still have to find 2A and 2B, or A and B. So, all right, next find A and B. And, you know, we have 2A is equal to P over 1 plus E minus a negative, so plus P over 1 minus E. We have 1. So we have P times 1 minus E plus 1 plus E over 1 minus E times 1 plus E, so 1 minus E squared. 1. E's cancel, so 2P 1 minus E squared. So that's good. A is equal to P over 1 minus E squared. Now, B is a little trickier. So A we have. To find B, we have to do the following. We have to take R of phi and find the angle at which, at which we have that star there. So we have to find this angle here. And then we can find what y, the maximum value of y is. So to find B, calculate y max. Now y is equal to r sine phi. So y is equal to P sine phi over 1 plus E cos phi, right? And if we differentiate, if we do dy d phi, we have P cos phi. In fact, we'll factor the P out. Okay, we have P times cos phi over 1 plus e cos phi plus sine phi times minus 1 plus e cos phi quantity squared, and then the inner derivative would be minus e sine phi. So we're trying to set this equal to 0. So we have we multiply by 1 plus e cos phi, so we have cos phi plus e cosine squared phi plus e sine squared phi over 1 plus e cos phi squared. So that's a derivative, so this is supposed to be equal to 0. And this is nice, we're going to have cos phi plus e, because cosine squared plus sine squared is 1. So cos phi plus e is equal to 0. Cos phi plus e is equal to 0. So e is cos phi is equal to minus e. And now we can go into y. So y max, which is what we're looking, which is going to be our b, same major axis, is equal to p 1 plus e times negative e, so 1 minus e squared. Now this sine of phi, we're going to call square root of 1 minus cosine squared. Okay, 1 minus cosine squared. I'm not going to write it down, I'm saying it. 1 minus cosine squared or 1 minus cosine squared. So it's square root of 1 minus e squared, right from that. And now we can cancel square root from the denominator, so that is equal to p over root 1 minus e squared. So now we're all set. B is equal to p over root 1 minus e squared. Now the last thing we need, let's check the clock again. The last thing we need to set up all these values is the distance from the origin to the star there. Okay, the distance from the origin to the center of the geometrical center. Okay. So I'm going to erase this calculation because I want to have all this stuff right here. Okay, so get the calculation. Good, you got that? Fair and square. Finally, distance center to origin. We'll call it D. D. Okay. And what D would be A, which is half of this thing, minus P over 1 plus E. But A is equal to P over 1 minus E squared minus P over 1 plus E. So we'll multiply 1 minus E, 1 minus E is equal to P over 1 minus E squared times 1 minus 1 plus E, right? Minus P plus E equals E, P over 1 minus E squared. So this distance here, very important, is E times P over 1 minus E squared is equal to E times A. So for a circular orbit, this E goes to 0, and then that distance goes to 0 as well. Good. Now we got pretty much everything. So now I can formulate the remaining part of this homework problem. Okay, I'm going to erase this again since you guys can have that. Okay. Show that P over 1 plus E cos B is an ellipse. Now, when we think of an ellipse, we're thinking x squared over a squared plus y squared over b squared equals 1. Okay, the equation of the ellipse. But not so fast. This would be a big error because our x is with respect to that origin and not the center of the potential. So we actually have to write x plus a, no, x plus d squared over a squared plus y squared over b squared equals 1. So we have to show that this here works, and again, if you multiply, this is, so let's write r equals P over B cos B. So if you multiply this with the cosine of phi, you're getting your x, and if you multiply with the sine of phi, you're getting your y. And then you get a mess of cosines and sines and what have you. And when you get the equation to balance out so that you've got a 1 on both sides, then you can declare victory. Because then you know that the thing's an ellipse, and at that point we can prove all 3 of Kepler's laws, right? At that point, you have Kepler's first law. And then we'll get Kepler's second law, Kepler's third law, and then we'll have that all wrapped up. And then there'll be other formal interesting things in the theory of central force as well. But this one, you know, you want to knock this one out and make sure you got all the steps. And this is really key here. So we're talking x cos r cos phi, y r sine phi, where this is your r. And of course P will be common to all, so that'll cancel away right away. And the A's and B have P in them as well. So P will cancel everywhere, and it'll just be a combination of sines and cosines and E's squared and so forth that you finally have to work around with so you can show this. So we have that, we have the integration, and this I think is a good place to call it a day. Let's see here. Sure. Yeah, next time we'll keep going through with Kepler's law and some other interesting central force applications. Okay, good. See you guys next time.